This video is an introduction to infinite series. We're just going to touch on some basic things. We'll start our notes with some definitions. First of all, an infinite series would be a sigma notation or summation notation series, but defined from k equals 1 all the way to infinity. There's the infinite part happening, of some given sequence we'll call a sub k. And as we know by now with this definition, this means we're adding up a sub 1 plus a sub 2 plus a sub 3 plus, well, it goes on forever. That's the whole point of it being infinite. Let's also recall the definition of a partial sum, S sub n. That's defined as the sum of the first n terms in a sequence. Furthermore, let's let L be a finite number, so just some non-infinite number. It turns out that if S sub n, that's this partial sum, approaches, that's what the arrow means, approaches, it means it gets closer to, right? So approaches L, as n approaches infinity, then we say that the series converges. That's just a definition or vocabulary word. So in other words, if when you let this infinite series go on and on and on, if it actually approaches some finite number L, then we say it converges. If an infinite series does not converge, then we say it diverges. I think that got cut off a little bit here. That's the word diverges, which just means it does not converge. Now we're also going to add a definition, which is the sum of an infinite geometric series. We've already discussed geometric sequences. Now we're talking about a series, which is when you add up all the terms of the sequence, and we do so with this summation notation. Now it turns out that if the absolute value of r, remember r is the common ratio, and a geometric sequence definitely has a common ratio. If the absolute value of it is less than 1, then we say that this geometric series, which is the sum of all infinitely many terms, converges. Furthermore, we know the equation of the sum, which is a over 1 minus r. Now that's interesting. If you recall the definition for the nth partial sum of a geometric sequence, which we have in a previous topic, you could look at that one and find a very close similarity with this formula. Okay, that's if it converges. Now, if the absolute value of r, the common ratio, is greater than or equal to 1, then it turns out that the series diverges. Let's try some examples where we want to determine whether the infinite geometric series is convergent or divergent, and then if it's convergent, we want to find its sum. Well, as we just said in our definition above, the way to find out is first of all to find out the r value, the common ratio. Let's take a look at our first example of a series. This one's listed as 2 over 5 plus 4 over 25 plus 8 over 125. And notice we're given that this is a geometric series, which means we can assume that if I take any term and divide it by the previous one, I should be able to get the common ratio. So let's just pick on the first two terms. If I take the second one, which is 4 over 25, and I divide it by the first one, which is 2 over 5, okay, we'll do a little fraction kung fu here. This is really 4 over 25 times 5 over 2 if I flip this second fraction upside down and multiply. Of course, we can reduce this. The 4 over 2 is really 2, and the 5 over 25 is really a 5 down below. So it turns out that 2/5 is our common ratio. That's r. Okay, well, if that's the case, remember our simple test is to determine whether the absolute value of r is less than 1 or greater than or equal to 1. Well, clearly 2/5, even when put in absolute value, is less than 1. And that's the case if you recall from our definition above, which tells us that this series converges. Now that means we can actually find the sum, as we said above. Our sum formula is just a over 1 minus r. Well, a is the first term, and that happens to be 2/5 in this example. So we could say 2/5 over 1 minus, we already found r to be 2/5. Okay, and simply reducing this will give us the actual value or the total sum of the entire series. With a little calculator magic, it turns out that this reduces just to 2/3, which means, given this formula, that's what the total sum turns out to be. Notice that's like the L number, the finite number that this series converges to. Let's take a look at a second example. This sequence reads, or series reads, 1 minus square root of 2 plus 2 minus 2 square root of 2 plus 4 minus ... Okay, so clearly it's an infinite series given the dots at the end. And we want to test, now we're told that this is a geometric series. We're testing simply whether it's convergent or divergent, which means we have to find the R value, the common ratio. As we've been discussing, this will be found by taking any term and dividing it by the previous. So again, you could pick any of these terms, but if I just pick on the first two, those numbers are the smallest. The second term, actually, remember, you include the sign in front of a term with it, so that second term is actually a negative root 2. Dividing by the previous term, the first term is just 1. That means my common ratio is negative square root of 2. Now, if you go back up and check on our test, we're looking for the absolute value of R, which for this example is the absolute value of negative root 2, which happens to be root 2, and we're trying to compare this number with 1. Well, if you understand the square root of 2, it's like 1.4 or something. You can approximate that with a calculator. The point is, it's larger than 1, and if it is, that simply means, according to the test above, that this series is divergent. And if it's divergent, that means it does not become equal to some finite number, which means we cannot find the sum, and so we simply say that it's divergent.